Hey, everybody, this is Larry. This is day 30th. Is that the last day? How many days are there in January? Huh. Hmm. All right, well, no, there's another day. The Leetcode Day Challenge. Hit the like button, subscribe, and join me on Discord. Let me know what you think about today's prompt. Today, I am a little bit more healed, I want to say, but I'm not actually honestly sure. I think in the morning, in the morning it is more painful, and then it gets a little bit better during the day. So I don't know. I still have a race to run in 4 days, which uh, I mean, obviously, I'm not going to hit that PB, but I am trying to walk it for credit. So we'll see. But yeah, I. But yeah, I am able to walk today a little bit more with the help of a crane cane. So anyway, today seems like it's going to be a hard problem. So let's dive right into it, right? For 24, because I'm hungry. That's also the other part of it is that I'm hungry. I want to finish this and eat. 2493 divide nodes into their maximum number of groups. You have n nodes, undirected graph, edges, bidirectional graph, bidirectional edge. Given graph may be disconnected. Okay. Divide the node into so that exactly one group. Oh, I want to say really quickly that I don't know. I have to figure out what I want to do on this channel. I mean, I know that's I've had this channel for years, so because there are times where I read the thing word from word, but people also always ask me how do I read so fast, and the answer on like during a contest or something, and like reading fast is I wouldn't say it's prerequisite, but it definitely helps with your speed, right? If you read fast, then you solve things a little bit faster. And honestly, the way to read fast in general is not to vocalize it. Uh, and sometimes when I read for you, it's so slow that I don't remember what I read because it's just so slow. Like I didn't pause in my head. But sometimes I read too fast and it doesn't pause in my head. So maybe it's just me being old and senile. But anyway, all this is recorded live, so that I want you to see a realistic. That's always my goal because you can watch someone explain any solution anywhere, right? Like you don't need me for that. Why come here? Look, listen, it's fine. Watch another person's channel. You can read it, watch as many channels you want. I don't care, right? I don't make money from this. But the way I bring it is that I want to show you live and also in a reasonably quick way. In that I'm relatively good, quote unquote. You may debate that. That's fine. But that and have some explanation in the as to my thought process, but also explanation a little bit, right? But honestly, the explanation is not like that's not unique to me, right? Like and for each problem there may be like 4 different explanations. I'm not going to explain it 4 times. Sometimes a certain explanation, a certain visualization may help you solve it more than other people's, right? So get different ideas, get different visualizations, and play around that. Anyway, so this is live, so if I take a while, my apologies, but that is intended. Well, the taking a while part is not intended, but the live part is. Okay, anyway, so we have a graph. Okay, we have edges. We want M groups. Each node in the graph is in one group for each pair of nodes. Okay, this part I have to actually slow down though. Every pair of nodes in the graph that are connected by a sub I, b sub I, if a sub I is belonging to the index x, and b then x sub. Okay, so basically, the group index has to be at most difference 1, right? Return the maximum number of groups in which you can divide the nodes. Return -1 if it is impossible to group the nodes in the given conditions. Okay. I think the first thing, my first thought, and I don't know this one immediately, just to be clear. My first thought is whether this is a coloring problem, right? In graph, there is this idea of colors and so forth, right? And I'm not quite sure. For example, here, I guess, well, I mean, it's not quite, it definitely is not quite the coloring problem, right? Because here in example 1, technically you could reuse the same colors that are not in the same group, which in this problem you do, right? Like in a regular coloring problem, group 1 would be in group 3. I mean, group 1 and group 3 would be together, even though they're not connected, right? But in this problem, clearly, they would be in separate groups, and we have to, or at least we have to count them separately. Okay. So n is 500 is interesting, maybe. I don't know. I don't know yet. Edges is 10,000 is also maybe interesting. It's small enough. I don't know what that means yet. Okay. So this is a hard problem. I don't know. I don't have any idea about this problem. I do vaguely remember seeing this just because I feel like it feels familiar, but I don't remember the solution. I never remember solutions. Not never, but like so because I trust that I can solve them if I see it again, which hopefully I do, even if it takes a while. And we're already 5 minutes in. I haven't really started yet, but yeah. Okay. So, my first idea is, okay. I mean, let's say complexity doesn't matter, right? Maybe that's where I want to start. I just want to kind of explore this problem a little bit, right? And how I want to explore it is just by playing around and try to figure out these properties. We always talk about properties. Sometimes I talk about invariance, which is related to properties depending on the problem, right? And I know we all want the optimal complexity, etc. But sometimes, for me anyway, to have a visualization to play around these ideas, I would like to maybe do something like, okay, so let's say complexity doesn't matter. What would be something that we could play with? Do we even know how to solve this if complexity doesn't matter, right? That's step one. And in general, I have my notebook here. Oh, drop something though. And it's just like a regular notebook where I just use a pencil on it. Obviously, for this channel, I don't actually use it as much. That the obvious part being that because I just want to show you what I'm doing. Otherwise, it's just like what I'm gonna do, like do. I mean, I guess I could do it, but you know what I mean. But yeah, okay. So how would I think about it? Is like, for example, I'm just trying to visualize example 1, right? And okay, let's say if we brute force on the node as the root, right? Like, my question is, if we have a root node, is everything forced, right? And what I mean by that is that, okay, for example, here we start with 5, then everything is forced, right? Actually, let me bring up drawing board. Maybe I do want to draw for this one for maybe obvious reasons. But yeah, I still don't know, just to kind of give you an idea, I still have no idea how to do this yet, or like, I don't have any idea. There, does that show up? Okay, good. Okay, so maybe like my idea is that, okay, what if it's forced? Or rather, is it forced, right? For example, let's say this same tree, or sorry, this is not a tree, it's a graph. We start at 1 at the root, right? Or 1 at the start. Then now you have to do 2, 4, which is the same, right? But also 5 here. And then now, 2, 4, 6, 3. Am I missing something? I think there is part of every node that connected. If it belongs on each node in the graph connects to one group. Sorry, which each node is in one group. Oh, we want to maximize. That's why. Okay. Yeah. Sorry. I guess I misunderstood this one. Because if we don't have to maximize, or for some reason I thought it would be minimized, even though obviously I read it a few times, because it just feels more like a natural optimization thing. But maximize is interesting, because I guess this is a valid answer then, right? Just to be clear. Like, I mean, or it's not the optimal answer, but it's a valid answer, right? So I just like to play around with ideas for now, because I don't think I have anything yet. But I guess is everything forced? I guess so, right? Everything is forced in the sense that if you have a root, then everything in the next thing has to be there, because there's no previous thing, and you have edges, and it can only be one group away, right? So in that sense, everything is forced once you define a root, right? So yeah, maybe you have 2, then now it's next to 1, and 2 is next to 3. Maybe I won't draw a circle because I don't know. 2 is next to 6, right? Ooh, No, that's fine. 1 is next to 4. I'm pausing not because I have trouble. Because I'm just thinking about other cases in which, like, I'm thinking about other input cases where, like, where it just makes it a little bit awkward. So that's what I'm doing right now. Because I mean, we can create, this is 5. What am I missing? 6 is 2 and 6 and 4. So this would actually be 6 and 4. 2 and 3. That 1, 2, 3, 4, 5, 6. Right? I don't know if I missed an edge, but that's the general look, right? So that's going to be 3. And the reason it's forced is because for every node, right, you only have 2 groups it can be, right? So this is some k, so it'll be k minus 1, k plus 1. So then every node that's connected to 2 has to be, either on a k minus 1 or a k plus 1, right? But did I draw something obscene by accident? I hope not. I don't know. Maybe if you have imagination, that's up to you. But the thing is that if this is the root node, then the minus 1 doesn't exist, so it has to be forced to be k plus 1, right? Group. And you could do that inductively. So what is an impossible case, right? Impossible case, I'm thinking of like maybe a k3, right? As in like maybe like 1, 2, 3, something like that, right? Because then now if you do 1, I'm drawing all over the place, sorry friends. You draw 1, then now you're forced to draw the 2 and the 3, but here they're connected. Oh wait, it's connected, fine. If A belongs to the group with index X and B belongs to the, I guess that's fine actually, right? I don't know if that because it's not exactly 1. It is, oh no, it is exactly 1. No. So that makes it wrong, right? So I'm looking at the problem. It has to be exactly 1, not equal to 1. So this is impossible, which is k3, right? And so if for those people who may not know graph theory terminology, this just means a complete graph with 3 nodes. A complete graph being a graph of everything look at each other. Is that the only case, or? I think so, because everything that's not k3 is 2 colorable, and if it's 2 colorable, then you definitely can have this, right? Or k3 or more, obviously. I mean, just because, well, I mean, yeah, you could say k4 contains a k3, etc., right? And the reason why I'm thinking of this is that I'm thinking about the impossible case, right? Now that we root out the impossible case, then in theory, we can root at every node and then try it, right? If that's the case, what is the complexity? Let me take a look real quick. 500 times 10 to the 4th. What is 10 to the 4th? 10,000? So 500 times 10,000 is kind of close, right? But like that's 5 million, I know, but I want to calculate. Okay. But I feel like that's it, right? So we just have to show that it is not K3. Or there's no K3s maybe. Am I confident about this? But if complexity doesn't matter, right? That was our caveat, is that then we would have a solution because we just brute force on the first node and then everything else will just give you an answer, right? And then the rest is just to check. Right? Yeah, I mean, I think everything is forced in a way. I mean, I think there are tougher cases, or not. I think it doesn't have to be a K3, actually. I think K3 is an example, but not maybe the example, now that I think about it. So you can't just check for K3 and be happy, because you can have something that's a cycle of length 5, right? So it doesn't have to be a K5, it just has to be a cycle of length 5, right? For example, if you have 1, 2, 3, 4, 5, oops. Okay, well, mistakes were made. Okay, there you go. Right, in this case, if you take any node, then 1, 2, 3, 4, and then 5, but 5 has to be connected to 1, which is impossible, right? Is it? No, it is. Just by parity, right? Because actually, I mean, I drew this wrong in that, no, I mean, I didn't, I drew it wrong, but also not, I suppose. Like, I drew it wrong in the sense that you can actually compact this to, oops. Like 1, 2, 3, 4, and then 5. You scroll up, right? Like this is node 2, this is node 3, node 4. So you have only 2 colors, if you will, or 2 groups. But then the 5 has to be. It cannot be in either of those groups because it's just 1 and 4. Given the that's not a K3, but it's just an odd cycle problem, right? Okay, which we can figure out. So okay, so I think the idea is just. And maybe we just kind of try it for every node. If it's 5 million on Leetcode is a little bit tight, honestly, because Leetcode is silly. But I don't know. Let's YOLO try it, right? So yeah, let's convert this to an adjacency list, right? And then is it 1 indexed? I guess so. Okay. I wish Leetcode was consistent. Just have 1 index or 0 index and not like change it every other problem. I don't know. It's kind of awkward. But yeah. And also because I prefer 0 index, I'm just gonna do right. And then yeah, for I in range of n, maybe best is equal to max best of calc of I. I'm lazy with the naming. Okay. Maybe -1, but we also want to. Yeah, maybe that's fine. I don't know. Maybe we can optimize this a little bit, but it won't be like a complexity optimization. It'll be like a constant optimization. And you have X, right? So start group 1 with X, and then go as far as we can, right? And that's it, right? So now we start with yeah, it's gonna be like a shortest path thing, right? Yeah, I mean, I think shortest path is fine. With validation and stuff, right? So yeah, D is you go to -1, maybe. I don't know. We'll figure it out. But yeah, so okay. We have distances is equal to infinity times n, right? Oops. Okay. 18 minutes in, we're not so bad. Well, if this is right, it's not so bad. Who knows? Okay, right. Okay, so the first thing is that, okay, if I mean we want to do the shortest path part, right? So if distances and this is a breadth first search, so every node that we look at or want to look at is going to be infinity, right? So okay, so that means that if distances of v is equal to infinity, then we set it equal to distances of now plus 1 and q dot append v, right? However, if it's not infinity, that means that we've always seen it, which is fine. But we also, the thing that we want to check is parity. I'm just thinking through an edge case that I have. I mean, parity is fine, but I'm also thinking about an edge case where of returning the answer, right? Because I was thinking about, okay, as we said, a cycle of length 5 is bad, but a cycle of length 6 is good, right? Because you can imagine that is 1, 2, 3, 4, 5. Oops, 6 is good, right? And then let's draw it out. And I guess, also for those celebrate, Happy New Year, Happy Year of a Snake. I guess we have a snake eating his own tail kind of thing going on. Anyway, okay, yeah. So that's fine. That's not what I care about, right? Like we knew that was a good one. But what is the number of colors for this one, right? I guess it wouldn't be 2. Like would it be 2? It may be 2 just by coincidence. But here we would draw 1. We actually have draws 2 and 6, so we actually would draw this a little bit differently. This is 3, and then this is 5, and then this is 4, right? So this would be the breadth first search look at it, and this would have 4 colors, which is fine, I think, right? Oh, that's what we want. Yeah, okay. So then now we have to check that if it's not, then we want to check that the distances of 3 mod 2 is equal to the distances of now mod 2, right? So if this is not the case, then we just return -1 because then that means that something about the graph is off, right? Because the connection from now to something that we've seen before is no bueno. Yeah. Otherwise, that's good. That's it. Otherwise, we can just return max of distances if that never happens. I think that's right. Maybe I'm missing one more if statement or something like that, but I think that's in general the idea I want to do. Okay, well, that's no bueno. I mean, the only way that... Oh, well, maybe not. Maybe it's this. Okay, let's see, right? We just don't well, we don't get here, so that means that this is actually terminating here. Maybe it's the infinity stuff though. No, we know that it's not. Okay, let's point it out then, right? Oh, I didn't do distances of x is equal to 0. What a new mistake. Okay. Still not... I mean, we need to fix that anyway. Okay. So 0 and... Oh, no. Should it be the same? No. If they're next to each other, that means I messed up. But in a good, easy way. I just kind of was lazy about this one, right? What I mean by... I have the idea relatively right, but I got the opposite, which is that they have to be, if they're equal, then they cannot be next to each other, right? So actually, this is the, that's the condition. So if they're, okay, well, it's still wrong, but a little, okay, but it's a little bit, at least it returns something reasonable, right? All right, let's see. Okay, 5 is 3. Why 5? 5, 1, 2, 4. Oh, because I start at 0, that's all. Okay, I think that's actually it. Yeah, that's not so bad. Maybe. I mean, I think the examples are kind of terrible. So, like, am I confident? No, not at all, right? So, let's at least... I've been lazy a couple of days, so let's at least add the 2 examples that we talked about, and then I'll still be lazy, but at least slightly less lazy. Okay, and the only other case that I worry about is like n is equal to 500 max case, but whatever. Oh no, I'm returning infinity. Oh, that means, because it's not connected. That's what it means. It even tells me that somewhere. I think I read it. Yeah, notice the graph may be disconnected. Okay, well, what happens if it is disconnected? I actually didn't think about that one. Whoops. I was focused on the the interesting part of the graph. So I mean, it could be interpreted both either way, meaning that, well, in that case, then I mean, it's just annoying. That's all, because that means that now, let's say you have a forest, right? I guess it's not a forest, but now you have two graphs within two connected graphs. What does that mean, right? Well, it's just the sum of all the graphs, so, or sum of the max components of all the graphs. So it's just very silly. Okay, fine. How do I want to fix that? I actually did forget about this part. I mean, I remember reading it, but I just never thought about it. Okay, because the idea here is that if you have, like, whatever, let's just reuse this one, right? Let's say we have another 7 and 8 node, then now you have what is it, four colors here and 2 colors here, right? So I mean, it's not that hard. You just have to add and connect the components and then solve for it. And I'm just being a little bit lazy and try to figure out how I want to write it. How do I want to write it? I mean, definitely this part, not quite, but oh, did they give us an input? Apparently, the first time I did it, I did not make this mistake. But let me just put it there. I guess it's so big that I don't care about it. Okay, fine. Like, is that? Isn't there like a use? Oh, there it is. Use test case. Why is that empty space there? Oh, I just deleted the return statement, so it's just not returning anything. But okay, so yeah, how do I want to write this? I mean, we talked about connected components all week. It's not that hard, but I'm just a little bit lazy. Well, first we can just convert this to what's it called? Collections dot default dect. Lambda is infinity, right? Because then now you can just return max distances. But then but yeah, so now this will work. I mean, it'll give me the wrong answer because we don't solve for it, but because in fact it just looks like that the input is just a lot of different components, but at least it should take care of that part. So then now we just have to do it by component, right? Yeah, I mean, that's not bad, I suppose. It's annoying, but not bad, right? So yeah, okay, so if done, or if not done sub I, something like that, and then done is equal to force times n, and then here, we want to say done of now is true. I think that's sufficient, except for that if with one connected component returns -1, then we have to do it, right? So it's actually now this, but maybe, oops, r is equal to calc sub I. If r is equal to -1, we return -1. Otherwise, we just add it, right? I think that's fine, roughly speaking. Maybe not. X, Y, why is this off by 1? Is it off by 1, or am I just... Well, it's off by 1 on one input, but it may be even worse on the other ones. Actually, it's right on this one, so why am I returning 3 then? What else did I change? The done does nothing except for that we don't... Oh, I'm dumb. Because it only calculates it once for this graph, which is kind of, I mean, it is actually working as intended. It's just that my intentions are bad, you know? It's like, what's that meme? I did all the math, but boy, was I bad at math. Now, yeah, okay. Now, this doesn't make sense. We have to do it for more than one component, right? So, okay, so we can just find the root of it, and then that's fine, right? So, yeah, so maybe we can do, this is a little bit yucky, but something like, best by parts is equal to right? Or yeah. And then now this will, what we want to do is this just return two components, the max of the value and maybe the max, the min node that we visit, right? So what is that? Min.keys or distance.keys, right? But the min version of that. And the reason is because in theory, on every, what you want is just to normalize the connected component, right? So you just want something that for every connected component, it's the same thing. And for me, it's just, it's fine. Like, and I just came up with it, right? Not to say that I haven't came up with it before. Like, I wouldn't be surprised if I did the same thing last time, but it's not something I remember. It's not something that, you know, but it's just like you ask yourself a question of, okay, I have a connected component. I have to have something to identify what's the laziest thing I can do. And this is the laziest thing I can do, apparently, right? So now you return the min of the keys, which are the nodes, and max of the values, right? So then now, okay, so do we care about done anymore? We don't, I don't think. And that's, no, I think I was wrong on that one. Right, so then now R is equal to, because we want to calculate to do best by parts is equal to min best by parts of, or actually there are two things, right? One is the group, and then R is the result. So then best of the group is equal to min best by parts of the group and or the new result, right? And that's it. Well, except for the -1 thing. So if R is equal to -1, we return -1, because if it's -1 for any component, it's going to be just no bueno. So then now we just want the sum of best by parts dot values, I think. Oh, I thought I deleted it. Collections. Okay, I mean, apparently we have a lot of typos going on, but you know, I think ideally, the theory is relatively okay. Did I not return two things? I do return. Oh, do I return? No. Calc. I do return two things, right? Do I have to make the tuples explicit? Do I also return other things? No. Oh, the -1. I guess for -1 then it doesn't matter. Maybe I'll just -1. Okay, still wrong answer, and now this one is wrong too. That is actually awkward. Best by parts of G is equal to, oh, we want max, that's why. It's awkward because once, I mean, this is not going to be right because I chose infinity as the default, but now we actually want 0. Yeah, okay. I don't know why I keep on confusing max and min, but whatever. Okay, let's now give it a spin. Hopefully it doesn't time out. Yeah, it looks okay, right? 1766 day streak, and we are muy bueno. What else is there to say about this one? Yeah, I mean, okay. Wow, this is slow. What is the complexity for this one, right? Well, for each node, we just run through the number of edges, so this is going to be V times E. There are some optimizations here, probably, but you could probably even do a tree rerouting, but I don't know if that's really worth. But I wonder how I did last time though. But yeah, the complexity is just, oh man, it's just V times E, right? For every node, we run this once, and for that node, this is, I guess it's V plus E, not just E, but it's going to be dominated by E, I suppose, because it's just, that's just breadth first search, right? Apparently I did slower than last time. What did I do last time? I mean, this is the same idea, except for I did it with top down. but I guess top down is faster. Why is that? And I was thinking about color. Oh, I see. Because I just did if it's not too colorable, then I return -1. So the reason why this is faster is just because I do an early check whether it is possible or not. I thought this would do it too, honestly. Because if you run it on, because you have multiple components. I don't know. I feel like, yeah, I feel like if it returned -1 for any node, it would this would just break early and then terminate, right? But I don't know. Anyway, the complexity should be the same. Maybe not. I don't know. Watch that video. But yeah, that's all I have for this one. Let me know what you think. Let's go over this real quick, actually. This is the adjacency list setup, right? This is to kind of, this is the calculation for each node. We just want to get the best answer if this is the root node. And of course, the reason is we have this G thing is because it could be for different groups, right? Meaning you have different connected components, right? And then you have to kind of combine them and get the best one. And then calc is just a regular breadth first search based on the thing that the invariant being that we will make sure that everything is, the parity is still right, and also the the shortest path is the way to go. And this is v plus e, of course, times O of v. Yeah, that is all I have for this one. Let me know what you think. Thanks for watching, and yeah, stay good, stay healthy, to good mental health. Happy New Year, everybody. I'll see y'all later and take care. Bye bye.